Let's go through some of the questions from exam 2. You'll see some of these on the final exam, so it'll be good to understand these questions as well as thinking about kinetics related to endurance performance. All right, so this is the first question. The swimmers will often use a swim parachute during practice. Which parameter of the drag resistance force would be most influenced by wearing this device? And so really I'm looking to make sure that you understand the drag force equation, which is, let's see if I can type it in, drag force, F drag, is equal to 1/2 rho, I'm going to just write it in, rho, density of the fluid, sorry, rho, CdA, I'm going to make that a subscript, V times V squared. I'm going to make that a superscript. That's our equation for drag force. 1/2 rho CdA V squared. And drag, we know, can either be resistance or propulsion. Rho is the density of the fluid. That would be the density of the fluid moving over the object. In this case, that'd be the density of water, which we know is about 800 times more dense than air. CD is coefficient of drag, and that represents how well the fluid moves over the object. And this one's a little tricky. It's there's a couple different parts to this CD. It's how well the fluid moves over the object in terms of how well how smooth the object is, or how sticky the fluid is to the surface of the object. We try to, in the case of reducing drag resistance force, we're trying to make this as smooth as possible, not having any stickiness of the fluid on the object. It's also a bit based upon the shape of the object, and we think of a teardrop aerodynamic shape. If you're looking at the teardrop from the side, that shape represents a lower CD than a round object, a sphere, or even a box type object. So that teardrop, where it has sort of a long tail, reduces this coefficient of drag. It reduces how, it increases how easy it is for the fluid to move over the object. So by adding this object, and it's going to be A is the frontal area of the object. So that would be looking at that raindrop, that teardrop shape from head on. So if you're lying down on the ground and you're looking at the teardrop falling on you, you would just see this sphere. You would see this, well, you'd see a circle. And that area of that part that's moving perpendicular to the flow of the fluid, that represents the frontal area of the object, and that's the A part of this equation. And V represents the velocity of the fluid moving over the object. Doesn't mean it's the velocity of the object moving relative to the ground. It's how fast the fluid's moving over the object. All right, so this question is really designed, and others in this exam, really designed to make sure we're understanding this equation, because this equation becomes important when we're dealing with swim technique, when we're dealing with cycling equipment or position on the bike, things like that. That this equation is critical, and to understand the different parameters in this equation. So really this question is asked, of these 1, 2, 3, 4 parameters, rho, CD, A, or V, which one is going to be influencing the drag force the most? In this case, it's going to be the CD. It's the shape of the object, in this case, adding on a, almost making the person more of a rectangle, and that is going to interfere with how well the fluid is moving over the object. If you chose A, that's not a bad answer either. But the reason why it's not A, frontal area, is because if you think about getting on the other end, on the head side of this swimmer, and looking at the swimmer, you would not see this red parachute in the back. You would only see the swimmer. Maybe you see a little bit of it, but really you're not going to see this this shape, this object, this piece of equipment from the front of the swimmer. And if you don't see it from the front of the swimmer, then it's not frontal area that's influencing the drag force. In this case, it's CD. Okay, so the correct answer would be CD. There's nothing we can do about fluid or the object. V is going to change naturally, and that's why I don't actually include this in the equation, because V is going to be influenced because CD is influenced, and the person can only generate so much propulsion force, which there's this interplay between propulsion force and resistance force, both related to drag force. And so the person ends up swimming slower when this drag force is increased because the propulsion force is still the same. All right. So the correct answer is CD, and that's a lowercase d in the answer. All right, next question. In the kinetic analysis of running, which force do you not include in the equation of F equals sum of forces equals ma? The whole point of this question is to make sure we're understanding Newton's second law, which emphasizes when we do a kinetic analysis, we only identify the forces acting on the person, not by the person in the case of running here. So although we may be interested in how much force the muscles are generating to push on the ground, we actually, to use Newton's second law, we actually measure the force from the ground pushing on the person, and we put that in our kinetic analysis equation. Equal and opposite, push on the ground pushes back on me. But to use Newton's second law, you only enter the forces acting on the object, not by the object. So that's what this question is designed to tease out. The force of the person pushing on the ground. Wait a second. Okay. I even threw myself off. Okay. This is why I don't always like test taking this way myself. I'm looking for the not, and let me bold that, because I was like, wait a second, this can't be the correct answer. It's just what I spoke against. So the force of the person pushing on the ground, I don't know why it's doubled up there, is the correct answer, because you do not include this force in the equation. Sorry about the pause there. The force of gravity acting on the person, okay, that's correct. You do include that. The force of the ground pushing on the person. These are forces pushing on or pulling on the object. And so these forces we put into this equation, we do not put in the force created by the object. So this is the correct answer because it's a negative question. Okay, next question. Below is an illustration of the vertical ground reaction force during running. Up is positive. At which point or points would the acceleration of the runner's center of mass be negative? Right, so this sort of goes back to still using this equation here. Let me copy and put it down here. The A part here, so the previous question was on the forces part. The M, which I often will include questions on, not only in this type of exam, but on the final, M is a measure of an object's inertia or resistance to change. It's measured in kilograms, and the inertia of the object is the same regardless of any force acting on the object. All right, so we often say inertia, and we might use the term weight. That's not correct. Weight is a force acting on the object, and we calculate weight by knowing the mass of the object, and we multiply it by the acceleration due to the force of gravity, the negative 9.8 meters per second squared. And that product of mass and times g is what we typically use for an abbreviation, represents the weight of the object. If we take that object and we measure the weight here on the surface of the earth, and then we take it to the moon, just a nice extreme example, I think we all know the force of gravity is less while you're on the moon versus on earth, and therefore you weigh less on the moon because mass times the acceleration due to the moon's gravity will be different. It will not be negative 9.8 meters per second squared. That's weight. However, the mass of the object, either here on Earth or in space or on the moon, is the same. It's independent of the forces acting on the object. So mass is a measure of inertia. Inertia is an object's resistance to change motion. An object with lots of resistance will have lots of mass. An object with very little resistance to change in motion will have very little mass. Obviously, there's a parallel to weight there because our negative 9.8 meters per second squared is what we're always entering for the acceleration due to gravity, and we're not going up in space or dealing with sports on the moon. But nevertheless, it's important to distinguish mass as a measure of an object's inertia and weight is a force. All right, and then the last parameter in this equation is A. That's the acceleration of the object. And what often is easy to forget is that it's the acceleration of the center of mass of the object. Now, a lot of times when we do, basic problems like in a physics book or what have you, we talk about forces acting on an object like a block or a ball or something like that. That center of mass is a fixed point, all right, because the segments are not moving. There's no segments moving on a box or a ball or something like that. But when we start dealing with the human body, the center of mass is not a fixed point. All right, you should have learned this in KIN 346, undergrad biomechanics. The center of mass is dependent on how the mass is distributed. It's the balance point of the object. So if I'm standing and I raise my arms up, my center of mass actually comes upwards. If I move my arms down, my center of mass moves downward. I don't need to move up or downwards, but the center of mass can change. A in this equation is the acceleration of the center of mass of the object. Okay, and it's something to keep in mind that when we're dealing with human movement, the center mass is not a fixed point in the body. We usually say it's around the hips, around the lower part of the trunk, but it's not a fixed point. All right, so that's what this question is really talking about is when will the acceleration of the runner's center of mass be negative? So when will the sum of all the forces acting on the object, when will the sum be negative? And you would have benefited by watching the equation or the videos on the ground reaction force during running. And when we're dealing with the vertical direction, we're dealing with the ground reaction force pushing up on the person and gravity pulling down on the person. So we're really looking for a situation where the force of gravity is greater than the ground reaction force. And there's two instances in this figure where that will be the case. Well, and here's that dotted line for body weight, which represents the force due to gravity acting on the person. And so all we're really looking for is any instance where the acceleration will be negative, which means that the ground reaction force will be less than body weight, less than the force due to gravity acting on the object. So we're looking for any point below this dotted line. So that's over here, and that's over here. This is heel contact, this is toe off, this is stance phase of running. This phase of running, this is where the center mass is slowing down, moving downwards. Oh, sorry, I messed up. The acceleration is negative here. So this is speeding up while moving downwards. There's a period where the foot contacts the ground, a very short period where you are still speeding up while moving downwards. Okay, and that's this region right here. Then you start to slow down while moving downwards, and then you start to speed up while moving upwards. And then at this very last part, right before toe off, you also have a period of negative acceleration, which in this case, it means slowing down while moving upwards. So right before your toe leaves the ground, you cannot push on the ground hard enough to overcome gravity, and gravity starts to win that tug of war, and acceleration will be negative in this region and in this region. This is speeding up, moving downwards. This is slowing down, moving upwards. Okay, and one more. Below is an image of swimming velocity versus time. The figure includes velocity relative to the left and right arm strokes, as well as the combined left and right swim velocity. During which phase, A, B, or C, would drag resistant forces be greater than drag propulsion force? So again, I'm asking you about this equation. And we're dealing with horizontal movement of swimming. So we have, in the way that I've set this up in class, we're really dealing with two forces, drag resistance and drag propulsion. Propulsion is actually pushing the swimmer in the direction of movement. The resistance is opposing that. Those two forces add up to mass times acceleration. Mass of the swimmer times the acceleration of the center of mass of the person. So this figure I just pulled from a paper, a book, where it represents the velocity based upon left arm stroke and right arm stroke. So that can be dissected a little bit further. This is the graph that this question is addressing. And on the y-axis is velocity in meters per second. And on the x-axis, I should have had time here. Maybe I cut it off when I copied this figure over. But this is time on the x-axis. When we have velocity versus time, we can start identifying the other kinematic parameter, which is acceleration. And you should be able to look at this graph and identify periods where acceleration is positive or negative. Anywhere where the slope of the velocity versus time plot is negative, acceleration will be negative. Anywhere where the slope of the velocity versus time plot is positive, the slope will be positive. So negative acceleration, positive acceleration, negative acceleration, positive acceleration, positive acceleration, negative acceleration. In words and describing the change in velocity, we have slowing down while moving forward, speeding up while moving forward, speeding up while moving forward, slowing down, moving forward, speeding up, moving forward, speeding up, moving forward, and slowing down, moving forward. And you can see in slowing down, the person's arms are not in a position where, in this case, he is not able to generate propulsion force. And we know the two forces, propulsion and resistance force, will add up to mass times acceleration. Propulsion force will be positive, resistance force will be negative. So we're looking for anywhere, let's see, during which phase would drag resistance forces, negative, be greater than drag propulsion force. So we're looking for where the negative force is greater than the positive force. Therefore, this product has to be negative. So really we're looking for any region in this plot where acceleration is negative. And in the way this question has been set up, the only region is region A. I could change this question again. I could move an answer over here to D. I could change some of the wording up here regarding, rather than forces, I could talk about acceleration. So those are ways that you want to think about these questions, is how to prepare the next time. Really, the key is to understand this equation and how to apply it. In this case, we're applying the use of this equation to swimming, and we're trying to understand the interplay of the propulsion force and the resistance force and how that will influence acceleration and how that acceleration translates to understanding change in velocity. Obviously, we want to have as less change in velocity and ultimately be able to maintain a higher velocity for swim performance. Okay, I hope that's helpful. F equals ma, Newton's second law, a big focus on this, and understanding kinetic analysis. All right, have a good rest of the day.